Want to talk to you today, and Wendy, I hope you're recording this.
I am.
Okay, very good. I want to talk to you today about molded parts, and just point to what you find in the Y14.8 standard. We have John Halk with us, who is a member of the committee, and so he's going to slap me around if I say anything wrong. And John, I hope you'll add as we go along also.
If I can, I will try.
Okay. In general, there's two approaches to tolerancing cast, forged, and molded parts. And as we called it molded parts, that's what the ISO committee does. They don't know how to spell mold. They spell it M-O-U-L-D-E-D. But they group everything into this category of molded parts, stuff with draft, and that includes forgings. So in our 14.8 standard, there are two general approaches. The preferred approach is to make most of the dimensions and or your 3D CAD model basic and use profile of a surface as a general tolerance. And I'll talk a little bit later about we'd like to see you model your draft also. The older approach that hopefully is phasing out is to use directly toleranced dimensions, those plus minus things. And to make that sort of work, you should add a general note that relates directly toleranced dimensions to a datum reference framework. Now that note, we'll see it in a little bit, that note used to be in Y14.5 and it was taken out. It used to be referred to as the bag of snakes. It was good that it related your dimensions to a datum reference frame, but still you would get tolerance accumulation and not really be sure sometimes where things were going, and when you throw in the angular tolerance, it was very confusing. So it's still there. We talk about it in 14.8, but I did survey the casting committee about a year ago, and several of the people there make castings and forgings, molded parts. And I said, what % of you folks are working off the 3D CAD model? Of the work that comes in, what % is really using the 3D CAD model? And they estimated about 85%. So you can see that this plus-minus approach, although it's covered and actually sort of featured just as legacy, hopefully will be going away. So here's a drawing, and we'll come back and talk more about this drawing later, but for right now I just wanted to show you that what we've done down here is that untoleranced dimensions are basic unless otherwise specified. So any of these you see up here are basic dimensions. I don't have to put the box around them unless they have a tolerance written next to them. And we also have some notes about draft, and we'll talk about those a little bit later. So this is kind of the preferred approach, or the even newer approach is model-based definition, where you leave off some of the dimensions, many of the dimensions, in fact. So those are the reduced dimension drawings, and I want to talk a little bit about those also as we go along. Then you have this other type of tolerancing of these parts, and you'll notice we have a note here that says dimensions are related to the datum reference frame established by datum features A primary. A is right here, and I probably should have said two surfaces and tied those together. So A primary, B secondary, which is this hole over here, and then C tertiary. So we've created a complete datum reference framework with an origin right over here along the axis of B. Then we have a linear tolerance of plus or minus 0.8, an angular tolerance of plus or minus 1 degree that can be problematic. Note about draft and fillets and rounds. And these fillets and rounds or corners are toleranced, plus minus. So this is kind of the older approach. Let's talk a little bit about some of the terms you find in the standard, and one is draft. And it's defined as the taper given to a part so that it can be withdrawn from the mold or die. There seems to be some question, and we haven't nailed it down in the standard, but some people say, well, draft is something that should be left up to the mold maker. It should be optional. But as we're going to model-based definition, it's more important to model the draft on your CAD model. So how do we do that? How do we get the designers to put that draft on? Well, the best thing is if they can work directly with the folks that will be making the tooling, making the parts. So is draft an optional thing, or is it a specific dimension? It's looked at kind of at both ways in the standard. Then we have this funny thing called a mold line. And a mold line is a line generated by the theoretical intersection of projected surfaces. And it's interesting, you'll find this term not only in molded cast parts, but you'll find it in sheet metal. Some companies, when they write sheet metal specs, will say where the surfaces project, because you have a bend radius in there. But if you project those surfaces to an intersection, they call that the mold line, which I found kind of interesting. So if the drawing references Y14.8, Y14.8 says that your dimensions apply at the mold line of features unless otherwise specified. So that is a default rule in 14.8 if you reference it. Now, if the parting lines are not indicated on the drawing, it is often difficult to determine where the dimensions actually apply or where the mold lines are. On simple parts you can tell, but on more complex parts, especially if your parting line is jumping around, that can be a problem. So on this simple part, I'm going to show you a mold line and some drafts. So we have our draft that you can easily see here. It's been put into the model. And about the only way you could pull this out of a mold is if you had a parting line right about here where this red line is. So the parting line hasn't been defined on the drawing, but I think I know where it is. And when I look at dimensions like this 105, this is to that older approach where we're saying dimensions relate to A primary, B secondary, C tertiary. So this is coming from a datum plane that was established by A, B, C. And it is going to the mold line that's shown down here. Let's take a little bit closer look at this. So if I extend this surface up and that surface over, this theoretical intersection is the mold line. And we have a couple people on the committee who have made molds, and I've never made a mold. I kind of questioned this and said, well, how do you find that theoretical spot? And the comment, oh, it's not hard. You just kind of measure along here and you can kind of figure out where that is. And then some other person admitted, well, I measure up close to it, and figure that's good enough. A little uncertainty there. But once again, Y14.8 says you see a dimension on a drawing and you reference 14.8, it's going to the mold line, and then draft takes over from there. So let's see, here's my primary datum plane. That was datum A up there, datum feature A. And here was a plane established by C. So we're coming from this plane over to that corner, that intersection, and then letting draft take off from there. The option to doing this would be to dimension to the surfaces, but if you think about that, that's pretty tricky because it'd be messy, I think, not tricky, but messy, because here I have a dimension at this draft angle, and if I want to dimension these other surfaces, if I have a fully dimensioned drawing, those would look like this. And I think you can see that if I start locating surfaces rather than these mold lines, I'm going to have a lot of funny looking dimensions on my drawing. So that's probably the main reason why a long time ago they came up with this idea, no, the dimension just applies at that one end of the feature, that mold line. A possible problem that I've noticed with this is with reduced dimension drawings where draft has not been added to the model and the parting lines are not identified, it's not really clear where the dimensions apply. And there's a very large company right now that's wrestling with this because they don't model their draft. And they're ending up with some very, very expensive parts, part of the defense industry. And once they're machined, their wall thicknesses are way too small and they can't handle the stresses when they're put into action. So I said, well, make sure you model your draft. And, well, we don't do that. And I said, well, show the parting lines. Well, we don't do that. Well, then you've got a problem. And often, once again, to show the parting lines, you're going to need to talk to the people actually making the mold. I had a good fortune many, many years ago working for a company that made cameras, and they made some pretty sophisticated molded housings for cameras. The tool designer was right next to the product designer, and they worked together on all the parting lines and drafts so that they knew it would still function and it would be real clear how to build that tool. Another term that we have in 14.8 is wall thickness. And if we look right down here, it says that the wall thickness is 4 plus or minus 0.2. The definition for wall thickness is it's an actual local size. And if you go to Y14.5, actual local size tells you that that's a point-to-point measurement, like a micrometer measurement. And what this wall thickness is on this drawing is a refinement of the profile tolerance. So let's see, we have our datum targets. Here we have A1, A2, and A3, so that establishes a plane here for A. B1, B2 is along this surface, so that gives me a plane through that set of targets. And C1 is on this surface, and that gives me another plane. So I know where my origins are. Then I have a basic 4 up here for a wall thickness. Notice that 9x by 4. And I have a profile of 0.8 relative to the datum reference frame. So that 0.8 is all over this part unless I state otherwise, which means you have a 0.8 on this surface and a 0.8 on that surface. And if that's all I did, if I didn't have this wall thickness here as a refinement, your wall could vary from 3.2 millimeters to 4.8 if you take the 0.8 here and the 0.8 there on both those surfaces. Excuse me just a second. By adding the note for wall thickness of plus or minus 0.2, that is a refinement. And it's saying, yeah, you can float around within this profile here and there, but wherever I throw calipers across here, it has to measure 4 plus or minus 0.2. So I keep a somewhat uniform wall thickness. That was a nice addition to our last revision of the standard. And I think Y14.5 is going to pick it up and put it in their standard. Draft can be very confusing. And some people don't even like to see the terms plus draft, minus draft put on a drawing. They said, you never know what it means. And I said, well, we're a standard, so maybe we should standardize it. So it has been standardized. Here we have 3 internal features, 3 holes. And this says 10 plus or minus 0.2 plus draft. Now that 10 applies at the mold line. So that would be down here, and then the dimension can only grow due to draft. So you're going to get something bigger up here very possibly than 10.2 because of the draft. This one says 10.2 minus draft. So on this blind hole, that means that it applies up here at the top, and you can actually get smaller than 9.8 because of the draft. So that's like an added tolerance in one direction, if you will. Now if you see DFT, INC, that means draft included. And that means you're going to have to get your draft along here within the limits of size. So you can't exceed 10.2 at the top or be less than 9.8 at the bottom. This one, unless you give a big tolerance, you got to be kind of careful with how you apply draft included. Now let me see how you folks are doing. I know some of you have microphones. This is on a boss, and it says 10 plus or minus 0.2 plus draft. Do you think that would apply at the top of the boss or at the bottom? That wasn't a rhetorical question. Anybody?
Are they sleeping?
I think so.
Oh. But this is riveting stuff.
I know. When they heard draft, they thought, you know, there's going to be some beer involved, I guess. I don't know.
Okay, hang on. Oh. Somebody says, I thought maybe I got an answer here. Hang on. Dave says the bottom.
Oh, the dimension can grow due to draft, and since it's a boss, it has to apply at the top, and then due to draft, you can get bigger. Okay, I'll give you another chance. How about this one? On a boss, 10 plus or minus 0.2 minus draft.
Dave says now the bottom.
Now the bottom. Okay. So there's your 10.2 at the mold line down here at the bottom. And then it's allowed to get smaller than 9.8 due to the draft. And then, of course, the draft included just says you have to get whatever draft you can within the limits of size. So that's for features of size, pretty much, you know, these directly tolerance dimensions. But what about if it's just going to a surface? There it gets a little confusing for some folks. Now remember, your dimensions originate at your datum, and this would have draft, the surface would have draft on it. And so the datum plane is going to be down here. And this is 10 plus draft. So that would apply up here at the top, and then it can grow due to draft. This one says 30 plus or minus 0.2 plus draft. So you'd think, oh, well, if that one applied at the top, this one applies at the top. But no, that applies at the bottom, and then the dimension can grow due to draft. So here I can exceed 30.2. And I think you can see how this can get to be kind of confusing, and that's why we created these illustrations and put them in the standard to really nail this down so it wouldn't be too confusing. And of course, this is with plus minus dimension. Yeah.
Yeah, is there any way to tie that draft into the parting line? Would that be of assistance? Where you're trying to break the mold and move it out, or am I off base there?
Well, somebody was talking about dimensioning at the parting line, having your dimensions apply at the parting line, but with the flash and everything you have there, that's probably not a cool idea. I don't know exactly what you have in mind, Frank. If you sketch something up, we'll certainly look at it.
No, I was just thinking of the angle that results from the draft if it's oriented towards a parting line, essentially, because it appears you're trying to facilitate the extraction of the part from the mold.
Correct.
That's what the draft's all about.
Yep.
And if it's going towards the parting line, shall I say, or the orientation's tied into the parting line, it might be a nice definition, but that may not suit. I can see where this would get real confusing real fast.
And that's why we created a bunch of figures to help explain. In fact, here, let me show you a couple more. Here's minus draft. Now, this is saying that the dimension, and just remember, it's the dimension we're talking about here, can get smaller due to draft. So that means this 10 has to apply at the bottom. Whereas the 30, the dimension gets smaller due to draft, so that applies at the top. And then this would be shorter distance from the datum out to here at the bottom. So I've seen people puzzle over this for a long time, so we added these figures hopefully to help standardize it, number one, and clarify it, number two. Now, what if it's basic? Well, same kind of idea. We're saying that, you know, if you have your draft, and draft here is 1 degree basic, and we're saying untolerance dimensions are basic, so this 10 is basic. I don't have to put a box around it because I've got the note. But this says 10 and then plus draft. So that 10 applies at the mold line up here at the top, and then it can get bigger due to draft. And the 30 plus draft, once again, that's on the dimension, so that can get smaller due to draft. Now, there's some people who say a lot better way than plus draft minus draft is to just have a note that says draft adds material, or sometimes people say draft adds mass or draft adds metal. Doesn't work real well with the plastic parts, but So let's see how that works, because that's a little bit different now. If you have a general note that says that draft adds material, as we see here, then this 10 would be kind of like a 10 plus draft, because the draft is going to add stock, and the 30 is going to be kind of like a minus draft, because it applies up here and the draft adds stock to the feature. So now don't think of the draft as being part of the dimension, it's the feature. What does it do to the feature? And it's going to add material. So I'd have to have my 30 applied up here. And so some people just shy away from any of this plus draft, minus draft, and go with this note right here. But there's times where you need to override this, where you need to clarify something. And so then the plus draft, minus draft can help. Not a bad note, though.
Don?
Yep.
Don? Dave asks, would it be okay to use 10 plus along with 30 minus so all measurements would be taken at the top of this part?
Sure. Absolutely. Yep. No problem there. You certainly can mix, not with this, because that would be like, well, they're both draft adds material, keeps them at the top. But you certainly can have some on the drawing saying plus draft and some saying minus draft. So, yeah, there's no problem with that at all. This could say plus and that could say minus, and we'd be good. A new symbol, a relatively new symbol that's been added to the standard is the parting line symbol that we see down here. And on simple parts, not a big deal to locate the parting line. On more complex parts, as you probably all know, your parting line can step all around. But we can use this symbol to indicate where it is, so then it's real clear where the draft is, at what direction the draft is going in any case. Another symbol that we have added is this all over symbol on one side of the parting line. So this is saying on the left side of the parting line, you have a profile all over of 0.5. And this happens to be the side that contains your datum features. So datum feature A is this surface, B is this hole, and actually at the nearest side of the hole, because I see a minus draft here, and C also. So on the near side, if you will, to the datums, I can control the shape better. But because of things like die closure and mismatch, I probably need more tolerance across the parting line. And so here we're saying, all right, all over this side of parting line, you're going to get a profile of 0.7. And this was a real nice addition. Now, how some people try to do it, and you'll see some ISO standards like this, and some U.S. companies did this, where they'll say things like, well, the tolerance is so much for the first 10 millimeters, and then it adds so much for each additional 8 millimeters or whatever. And then they'll say, and if it goes across the parting line, add so much tolerance. And if it goes to a core in a casting, add tolerance. And if it's from one core to another, add tolerance. And they're a terrible mess. ISO does that, and I have been with people that really support ISO drawings and that standard, and I've just picked out a distance and said, okay, what's the tolerance between here and here? And I've had a couple of their folks in the room, and all they do is end up in an argument over it. I was working with a very large corporation who had that in their standard, and I was able to talk them out of it. They finally got rid of it, thank goodness. So we need to reflect that, yeah, on the other side of the parting line, you need more tolerance, and I may need more tolerance in one direction than another. I'll show you that near the end of the presentation. So I think this was a real good addition.
Don, on some of the drawings that I work with where people have given this rate information of giving more tolerance as you go along, they accidentally, I say, have given away the farm without realizing it, because they've allowed so much tolerance to exist. It could go either way, too much or too little.
Yep. And I think we do need something that does a nice job of indicating sort of a rate, as you said. The further out I get, the more tolerance I get. And we have a way right now in Y14.5, but it's not a very good way. It allows you to draw phantom lines and dimension those phantom lines to show that a tolerance zone is non-uniform, that it's growing as you get further away from an origin. The trouble is you can't really do that on model-based definition, on 3D CAD stuff. So we have another method that's being proposed that will allow us to do it without using those phantom lines, and that may help some. But people just, as I like to say, get all wound around the axle when they try to find out or figure out what the tolerances actually are when they're doing that progressive kind of thing. Does the process act that way? Yeah. Well, here's another point. You know, I look at those as design guides. And so if you have a part that's 10 inches long, go to those charts and see what kind of tolerance you need over the 10 inches. And make that your largest tolerance. And then tighten up tolerances right up on the field of the drawing only where you need to. So what if you give a little more tolerance than the guide says as you get closer to an origin? If it doesn't matter, manufacturing will love you. Some other terms that we have in the standard. When we talk about a corner radius, we're talking about the outside corner. And we've brought the molded plastic folks into the fold, part of the standard. And most molded plastic folks will call that now a round rather than a corner radius, which is more common to casting or forging. So you'll probably see that word round added to the next revision. And then the interior corners are your fillets. You know, it's sort of like when you're welding, you fill it in there in that corner. So those are called your fillets. Probably everybody's aware of that. So we add notes
Don,
to the drawing.
This is John again. The 2009 standard now includes the word fillet, whereas before it never did.
Ah. Okay, you got me, John. What were we calling it?
They just assumed that R would be good enough to discuss these things.
Boy, I've got to look that up because I don't recall that.
In the 94, if you do word search on fillet, it won't be there.
Okay.
Fair to curve is there.
Okay. My memory is fading, I guess, as I get older, because I thought we had fillet before. But okay, it's there now. That's the good news. And I think we'll have round added for the next revision. Restraint notes are something that you want to add, especially to your molded plastic parts. But some of us were at a Y14.5 meeting, and a gentleman from General Motors was talking about, he didn't call them torque plates, that's what I'd call them. They call them that in the racing world. But a plate that they bolt on where the head goes on your engine block, and then they do their machining and honing, because they want to have the block distorted the way it'll be distorted when the heads get bolted down. Well, on this drawing, I have a restraint note, hopefully that reflects how the part will be used. It says dimensions and tolerances apply with part restrained to datum feature A simulator with a 4 Newton force applied to each of the datum D targets. So A is this face along here, B is this hole, and C is that slot. And it's saying when you inspect the stuff up here on this drawing, I want you to clamp it down. I want you to come opposite B and C here and apply the 4 newtons of force. And on a flexible plastic part, that's really advisable. It's also advisable when you have a restraint note that you have at least one or maybe a few tolerances that are checked in the free state. And we have that here. Datum feature A has a flatness that's checked in the free state. So without restraining it, you'd check that flatness just to be sure the part isn't too warped. Because when you restrain it, if it's too warped, you're gonna strain it when you restrain it, and strain causes stress, and stress isn't a good thing. We also have B is in its free state to check that perpendicularity, and C in its free state to check the position. So I would check those probably first, then I'd clamp the part down, lined up on these datum features, and then I would check the, oh, there's another free state. I missed that one. So we have the length of the slot also is free state, position of that slot. So then you'd check the other parts with it restrained. Good idea for plastic parts. More and more people are putting a general profile tolerance on their molded and cast and forged parts. You see I have a profile of 0.8 down here relative to the datum features. And I have targets, very common with castings and forgings and some plastic. And the question became, well, what happens to your profile tolerance if this profile applies all over this? As one member likes to say, it's kind of like a paint dip tolerance. You dip the whole part into paint, and that's showing you where the tolerance applies. But what happens right at those datum targets? So let's see, we have this part, and you can see the targets, and here's a little fixture to set up the part. And if you look down here in the standard, it tells you that right at the target, you don't get the profile. They're coincident, if you will. But as you leave the target, you do get your full profile. 0.8, so it'd be 0.4 up and 0.4 down from the plane established by the targets.
Don, Perry has
Yep.
a question.
Yep.
I was just going to type it because I had it up a while back and then maybe didn't see it. So anyway, can you go back one slide, Don?
Further?
I actually go back another. Yep. One more.
Okay.
There. That illustration that you have, those arrows where you have the free state before the modifier and the tolerance portion, is that specific to the molded standard? Because that's in conflict with the 14.5.
Uh-oh. Are the free states supposed to go after the M's?
After the modifiers, that's what the standard says. The 14.5 says.
Oh.
So we're following the modifiers.
You got
I
me.
just wondered if it was
No, we didn't change that around because in my mind it doesn't matter a whole hill of beans, Perry. But if those words are in 14.5, I'll switch this around.
Yeah, they're in 5.5.1.
Okay, I believe you.
Okay, I just wondered if it was different in the 14.8.
No, I missed that. Yeah, they're both modifiers, so that it's kind of funny that they say, well, it has to go after the modifiers because F in a circle is a modifier to the tolerance. So, sometimes we have some rules there that become pick and pepper out of fly poop, and I'd kind of put this one in that category, but I will fix it because the standard says that I will fix it.
And because at Tec-Ease,
It's never wrong to do what's right.
GD&T
I will fix
rules.
it. Okay. All right. So are we all clear on this? What happens with the
Just wanted to
profile?
clarify that.
What's that?
I said I didn't mean to pick on you. I just wanted to clarify that. So.
No, I appreciate it, Perry. Anytime. No, that's fine. Now, I'll just mention briefly, what if you don't have targets and you have a profile that applies all over? Well, at the datum features, you lose half of your profile tolerance. I don't want to get into it now, but there will be some discussion of that in the next revision of 5, I do believe. So you don't get to use all your profile tolerance if it's a full feature, but when it's a target, you do. But right at the target itself, there's a zero basic between the center of the profile zone and the target. Now, this isn't true if you use unilateral. If you use unilateral, then it would all be up here above your target plane. And then I just wanted to mention a few other things while we're talking about these parts. Sometimes people miss talking about some of the process effects that you get. So I'll just mention a couple of them. One is ejector pin marks. I have seen ejector pin marks ruin the appearance of a product. We need them to pop the part out of the mold, but I strongly recommend that your drawing have some sort of a note about ejector pin marks. Something that tells me whether the flash that you get around these pin marks is additive to the geometric tolerances and linear tolerances, or is it included within? And how much can it be additive? How much can it be raised, or can the pin mark be depressed? Another one is flash, and flash and gate, both of those. I'm illustrating some flash here around the part. There's the finished part, and the gate where the runner connects to your part. And once again, it's really nice if there's some sort of a note that tells me whether the gate has to be within the stated tolerances, or if it can be additive, and if it can be additive, how much. The same with flash. And another real common one is sync. So some sort of a note about sync, because you're going to often get it. And by the way, I've got this letter tray, you know, those in-out baskets, and I just want to mention something. I was visiting a friend. He was a manufacturing engineer at a company that made molded parts, and they made this sort of stuff, and then they chrome plated it. Well, he showed me a brochure. He didn't even show me the real part. He showed me a brochure that had a chrome plated plastic letter tray like this, and the ejector pin marks were right up here on the top. Instead of putting them on the bottom where nobody'd see them, nothing was said on the drawing, so all around here you had ejector pin marks. Now, those ejector pin marks have standing flash, and if you're familiar with chrome plating, that sharp standing flash will attract that chrome and really emphasize those ejector pin marks. And I saw the brochure, and immediately I said, what idiot didn't specify on the drawing where ejector pin marks should go? Fortunately, it wasn't him. But he said, yeah, I know, I'm not too happy about that one. So try to think about these things with this sort of part. One other thing I thought I'd throw in here is something that's being toyed with. Might be in the next revision of the standard. We now have degrees of freedom, and we can release degrees of freedom when you're setting up your datum reference framework. And we had another brown bag session about degrees of freedom, so I'll just hit this quickly. But if we talk about die closure and mismatch, here the animation is showing you what we would call die closure. As you shoot the material into your mold or die, it can separate a bit, and that'll cause that movement that you just saw. Also, you might not have beautiful alignment left-right, and that's known as mismatch. It results in your parts. You'll see a little step down here at the parting line due to mismatch. Now, the actual shape I can often control very well. It's just I have to somehow account for this die closure and mismatch. We struggled as a committee for many, many years on how to deal with this until this releasing degrees of freedom came along. And so now if you look at this profile on this side of the parting line, and that probably should be all over. There's an arrow right there. That's all around this side of parting line. It should be all over this side of parting line. The first datum reference frame constrains all of the degrees of freedom of the tolerance zone. So A is constraining U, W, Y, B is constraining V and Z, and C is constraining X. So that's just like a regular profile tolerance applied to the surface. But this lower one, this profile of 0.2, left out Y. So that's saying this tolerance zone of 0.2 is allowed to float up and down. It's restrained left, right, and front to back because we've included here Z and X, which would be the other translations. But it's allowed to float a bit up and down. So the result is that it's accounting for die closure here. Where die closure needed the bigger tolerance of 0.5, we're saying this thing could open and close 0.5. But mismatch-wise, it can only move around 0.2. So just quickly, we recognize that when you set up a datum reference framework, we have axes where the planes intersect. They're X, Y, and Z. And the movement along the x-axis is called lowercase x, that translation. Rotation is called U. Along Y we have the translation is Y and the rotation is V. And then Z, the rotation is W and the translation is Z. So we can declare what of these degrees of freedom are actually being constrained now. So once again, notice that in this lower segment, the Y has been left out, which means this is free to float up and down. So it can float up and down the 0.5 to account for die closure. But left-right, it can't move more than 0.2. So of the 0.5 tolerance zone, there's all this area or volume in here that is unused. You don't get to use that tolerance because of the refinement down here. And I can tell you that one member of the committee who's in forgings just flipped out when he saw this could be a new tool for him. He thought this was the greatest thing to come along. There, we'll let that thing float a little bit more. And that's what I wanted to talk about as it relates to molded parts. Any questions or comments from anybody?
John typed to me that he really appreciates the organization of these presentations and how well they're done. So good job, Don.
Wow, thank you very much, John. He didn't think you were going to read that out loud, Wendy.
Perry?
Anyone have any? Oh, yeah, Perry?
Yeah, Don, you were talking about specifying the 14.8 standard.
Yeah.
On our drawings, we specify the 14.5. Do we have to specify 14.8 on our molded parts drawing, or is that included indirectly through 14.5?
Some standards are included indirectly, but 14.8 isn't one of them. It does need to be specified if you want it to kick in.
But isn't 14.8 referenced in the 2009 standard of the 14.5, or that doesn't necessarily?
It's mentioned, but that doesn't invoke it. Like
Okay.
surface texture, I think, is one that is invoked, and the standards for drawings, sheet size, and line weight, and all those are invoked. But 14.8 is not, just by saying 14.5. Now, there's a movement to make that happen, though, Perry. As you and some others may know, ISO came up with an interesting little rule. They said if you have a drawing with any of our symbols on it, you've just invoked all of the ISO symbols, all the ISO standards. You don't have to say it on the drawing. Well, you know, a lot of the symbols are the same between ASME and ISO. They don't have the same meaning very often, but they look a lot alike. So now we're kind of, to fight back, we're going to come up with a rule that's about the same that says if any of the symbols found in our ASME standards, our Y14 standards, show up on the drawing, all of the Y14 standards are in play. But that hasn't passed yet, Perry. Yeah, we've had several discussions about this.
Since the symbols are the same, and you didn't specify it, how do you know which one would default to then?
Oh, what we're trying to pass is trying to fight what ISO is saying. And you're right, you wouldn't know. I mean, if we both have that rule, you don't know what standard to follow. And the reason we're doing it is we want the standards stated on the drawing. Now, the difference is, you know, our standards don't change as frequently as the ISO standards. And like our Y14.5 standard, if you wanted the equivalent in ISO, you're going to have to list about 24 of them.
Do you have a list of all those somewhere, Don, of the ISO standards equivalent to the 14.5?
I do. Yeah, I do.
Would that be something you could email me for my information?
I sure could.
All right, that would be very well appreciated if you could do that.
Okay. I'm making a note.
Yeah, Don, it's a great question. Just because a drawing references Y14.5, how do you know 14.100 or 2 or 3 for sheet sizes and line weights? How does that get in invoked? Is that in play type scenario?
Um,
And I've actually attempted to reference Y14.100 on a drawing, but that didn't make it very far.
hold on just a second. I'm looking something up.
Okay.
In all the standards, you will find right up front a statement, and it varies depending on the standard. In 14.8, it says, reference to this standard. Where drawings are based on this standard, this fact shall be noted on the drawings or in a document referenced on the drawings. References to this standard shall state, prepared in accordance with ASME Y14.8 2009. And Perry's going to say, well, if I say 5 and 5 references 8, but that doesn't invoke it, is my understanding. Now, what I'm looking for is another standard that does get invoked and see how the words are different. Like maybe metric sheet sizes. Just a moment, we're getting there. It doesn't have anything saying reference to this standard. So I may have to go back to 14.100. I may have to do a little research on it. But I know we've had the discussion in the Y14 meetings. But 14.1 doesn't say anything about it. And they've played with these words over and over and over again. References. The following list of publications referenced in this standard, when the following American National Standards referred to in this standard are superseded by a revision approved by the American National Standards, the revision shall apply. That's not telling me a whole lot. And the problem with saying that one standard invokes another is, what revision? What revision does it invoke if it's not stated? And that was part of the issue when you have you have a standard like sheet size, not much changes there, or line weights, but something like 14.8, a lot changes in each revision. I don't have a better answer for you, Perry, but I can sure try and get you one.
Okay, it's come up around here because we got some applications where we're going to use the concepts in the 14.8 standard, but now I have to determine if we have to put that in the. And I told them that I think it's already covered under the 14.5 that we have on our drawing, so I probably lied to them. I don't know.
I think you did, Perry, but I'm not going to tell them.
Well, that's why I figured nobody else is going to question it, so they just assume that it does. But I did want to know that. Because I think it's kind of unclear as to what other standards are invoked and which ones they're not.
Yeah, here's this is in the multi-view and section view drawings. The following documents from a part of this standard to the extent specified herein, the latest issue shall apply. And they're referencing the one on sheet sizes, metric drawings, line conventions, even an ISO standard on general principles for presentation. But they don't mention 5 or 8 or any of those. So this, I mean, if you mentioned Y14.3, it wouldn't invoke 14.8 or 5. We'll have to take a look at the words are funny, and I know they keep working on them. But it's really tough because if you wanted to invoke, let's put it this way, Perry. You want to say 5 and you say that invokes 8, I'm going to say to you, what revision?
In the 14.5 it says, in the event of a conflict between the text of the standard and a reference cited herein, the text of the standard will take precedence. That's what it says in 14.5. So if there's a conflict of another standard, it also says above that, it says, a more recent revision may be used provided there's no conflict.
Yeah.
So I guess if there's, it would be the latest. you can get the semantics, everything, but I was just kind of curious about what invokes all the standards that we use. Because we use the multi-view, the sectional view, the 14.3, 14.1, all those we use, but how do they get invoked? I was just assuming that since we mentioned 14.5, all those would follow because it's referenced in the 14.5.
Well, and I can research it for you more, Perry, or I'll tell you who's been in the mix of that is Jim Burley. Do you know Jim?
No, I probably know if I've seen him, if he's been at the meeting, but
okay. Well, I'll dig out what I can for you, and include that with a list of ISO standards. How's that?
Okay, that'll be good. I appreciate that.
Okay. I'll try and get the latest words because they keep changing them. Okay, anything else?
I actually have another question if nobody else does. I don't want to steal everybody's time.
Oh, go for it.
We have a standard for the molded parts and the forgings. Someone asked me about if there's a standard or going to be a standard for sheet metal parts.
Well, Perry, do you have a little time on your hands? There was a standard, and somewhere I have a copy of it, is Y14.10 on sheet metal. And it doesn't have to be a very thick standard, although you have to deal with the same issue we do about where dimensions apply when you have spring back and all that nasty stuff.
Okay.
But the main thing it should talk about is, in my opinion, the shear, the burr. When you apply a feature of size, does it apply to the entire depth of the feature, or just when you punch a hole, you know, about 30% of it will be your punch size, and then it rips out. So I think we need one, and it'd be reinstated. It'd be called Y14.10. All we need is some ambitious individual to say they'll chair it, and then find some people interested to serve on the committee. I can help you with that.
I don't know if I want to dig into that.
Well,
just a couple of things that you just said, Don, was we have some sheet metal parts that we have, and we stamp them out, and we have some other issues going on. In our drawing, say we conform to 14.5. Well, that says that that hole that we punched out, that size has to take place over the whole length, depth of the hole.
That's right.
So that's not very good for some of the parts that we make. So we had to take notes and say it doesn't apply to this section or that part. And then we were talking about...
I totally agree.
One guy said that he attended a seminar somewhere, I can't remember, it was a long time ago, about GD&T for sheet metal parts. And I said, what standard was it based on? He didn't know, so I didn't know. I'd never heard of a standard. I don't know.
Yeah. I've got a copy of it somewhere around here, and it was Y14.10. The trouble with it at the time is it was mostly recommendations for designing sheet metal, how close you should get a hole to an edge based on material thickness and how big a bend radii and all that. So it was more of a design guide than the standard that we need. But that could be brought back to life. We just need a chair and some members. And I think it's needed. If I didn't have so many committees going, I'd get on it.
Well, I might mention it to our guys that are dealing with sheet metal every day, and they might be ambitious enough to find one amongst them. So I'll check with them and get that.
I'll be glad to steer them down the right path if they want to do that.
Okay. Thanks, Don.
Okay. Anything else? Wow, that came out pretty nice, about 4 minutes to go. So I want to thank everybody for attending. And as always, I'm looking for ideas for these brown bag sessions. All the good topics are just about used up, I think. I don't know.
How about one of them, being targets on the part or the gauge?
Don't go there. Don't go there.
I used to like you, Perry.
Bushwhack.
Now, for anyone else still listening in, that I was embroiled in a big debate over that at the last 14.5 meeting, and it still isn't settled. So I think it's gone the way I'd like it to, but it's got to be cleaned up. Yeah, that would be a good one. I'll bet some folks from GM would attend just to heckle.
Yeah.
But seriously, if there's some topics you'd like to see discussed, I would really appreciate hearing from any of you.
I think any topic you pick is good, Don. I always enjoy these brown bag sessions, and I learn more every time I talk to you, no matter what it's about. So whatever you can't go wrong.
Okay. I will mention that the graphics that you saw here, we've added a supplement to our fundamentals text on molded cast parts. When we find ourselves in a company that is doing those sorts of parts, then we jump back into that supplement. So that has been added to our fundamentals text revision. So there was the commercial for the afternoon.
Good job.
Okay, Wendy, I'm finished.
I just got something. In a recent conversation, it was questioned how the mass standard impacts measurement when using an imperfect datum feature. Maybe that's a topic for another.
Well, yeah, that gets kind of heavy. I guess I would say it looks like the recommended routine is going to be L1 normal. How's that for an answer?
Magic.
What? No, let me say that you go back 20 years in the standard, and when you talked about a primary datum feature, it talked about finding an optimum position for a primary datum feature that was a rocker, or let's say it was a hole that wasn't a nice cylinder. You put a pin in there and the pin could rock around. And it said you should find an optimum position. Well, the math folks, when they wrote the standard, the math standard, took that to mean you could rock it left, you could rock it right, anywhere in between to find the optimum datum plane. And that's known as the candidate datum set. And that's how the math standard reads today. And they're charged now with changing that so that we have a best solution that simulates putting the part down on the surface plate. Well, the part could still rock on the surface plate, but they're looking at routines now, software routines, that'll give us an ideal or best answer, best solution. And there's one that's a relatively new routine. It's called L1 norm, and it is at this moment the most promising. But they looked at least squares, translational least squares, Chevy Chev, I don't know, there's something else in there. But this L1 norm will look to be the most promising. But there's some interesting work being done there, and there's some real good people on it. So I hope that sort of addressed the question.
I think maybe, Dave, did that answer your question? Yes, thank you.
Okay, and just do a Google on L1 space norm, and you'll find more discussion about the routine. I was surprised to find as much out there as I did. Okay, well, thank you, everybody. It was great seeing a bunch of you at the 14.5 meeting, and you're all welcome. You know, guests are invited to our Y14 meetings. So send in those suggestions for the next brown bag, and have a great summer.
All right,
Yep.
thanks, Don.
Thank you.
Thank you, Don.
Thank you, everybody.
Thank you, Wendy. Guys, have a great day.
Thank
you,
you
Wendy.
too.
Yep.
Bye-bye.